the next lecture will be based off these ideas here. So we want to give a geometric description to the set of all vectors that are perpendicular or orthogonal, because I guess we can include the 0 vector. So we want all of orthogonal. We want all the vectors in R3 that are orthogonal to this given vector 2, 3, 5. So here's that vector 2, 3, 5, right? Looks something like this. And so now, what are all, so here's some vector, right, this marker. What are all of the vectors that are orthogonal to this one vector? Well, this vector is orthogonal, this vector is orthogonal, right? They're all orthogonal. And so what happens when we collect all of the vectors that are orthogonal to this one single vector? Well, that should sweep out a plane, right? If you think about what's going on here, and I know this is a terrible illustration, computers do a better job, but given a fixed vector, if you look at all of the vectors that are orthogonal to this one, you sort of go around, right, around the flagpole here, right? So it sweeps out a plane, right? That's the set of all vectors that are orthogonal to this given thing. So how can we describe a little more rigorously, right, the set of all vectors that are orthogonal to this thing? So let's go ahead and write that down now. And at the end of this, the answer that we get, we should be able to recognize that thing as a plane using our knowledge of span. All right, here's this example worked out. So we want to find all of the vectors v. So we'll write the component form x, y, z. Find all of the vectors in R3 that are orthogonal to this particular vector 2, 3, 5. So remember, vectors that are orthogonal to this thing, what does that mean? It means when I take the dot product, u dot with v, I'm going to get 0. So if v is orthogonal to this thing, then that means v dotted with u has to be equal to 0. So what is that going to say about these numbers x, y, and z? Well, you know when you take the dot product of this thing and this thing, you get 2x plus 3y plus 5z is equal to 0, because this thing is orthogonal to this thing. And this is the dot product. And we know it's got to be 0. So now we can pick any one of these. So remember how to solve these equations, right? Here's a single linear equation, and basically we want to write down the solution set. There should be infinitely many solutions to this thing, so let's write them all down. What does it mean to say that 2x plus 3y plus 5z is equal to 0? Well, let's see if we can get a parametric representation for the solution like we did in the beginning of the semester. So you can pick any one of these variables and solve for it. I'm going to go ahead and pick x and solve for that. But you could certainly pick y, or you could pick z. So when I do solve for x, I get that x is equal to negative, right? So I'm going to take these things and subtract them over and then divide by 2. So I get x is negative 3 halves y minus 5 halves z. So now this tells us, right, if this relation is going to be satisfied, and that's what we need, that tells us a relation or a condition that we have to impose on the real number x, right? If this is going to be true, then x has to be equal to this thing. So let's go back to our original component representation of the vector v, right? It's x, y, and z, but what is x? It's negative 3 halves y minus 5 halves z. So instead of writing x, I'm going to write negative 3 halves y minus 5 halves z. And then just go ahead and recopy y and recopy z. But now you can take this thing and you run the usual vector arithmetic. So I can split this thing up as y times negative 3 halves 1, 0, plus z times negative 5 halves 0, 1. So that's how I got from here to here. And again, if you multiply, and then add, you will get back to this thing. So now, because we don't want to deal with fractions, y and z can be anything. So that means I can basically just multiply all of the entries by 2, and it's the same thing, right? As y and z scroll through all of the real numbers, the vectors that you sweep out will be the same thing as if you just take -3, 2, 0 and -5, 0, 2 and multiply those two things by all the real numbers. So as y and z scroll through all of R, these two expressions will be the same. And I would rather use this one because it doesn't have any fractions. That's the only difference. These two vectors sweep out the same thing, and I would rather just use the representation that doesn't have fractions. You can use this if you want, no problem. So now, what do we know about V? We now know that V, what we started with, is a linear combination of these two vectors, -3, 2, 0, -5, 0, 2. So now that means V belongs to the span, right? That's what linear combinations are. If you collect all the linear combinations of these two vectors, that's exactly the span of those two vectors. So now V belongs to the span of these two vectors. And now we've got the span of two non-parallel vectors. You can check that these things are not parallel because there's no scalar that you can multiply this thing by to get this thing, right? If there was a scalar that you could do that, like alpha, well then if I multiply all these three things by alpha, then in particular when I multiply 0 by alpha, I should get 2, but that's impossible. 0 times anything is 0, so I'll never get here. So this thing is not a scalar multiple of this thing. So these two vectors are not parallel. And so what does the span look like? We went over this. The span of two non-parallel vectors is exactly a plane spanned by those two vectors. So because these two things are not parallel, the span of these two vectors is a plane. So here's the plane, here's the set of all vectors in R3, right? This is the set of all vectors in R3 that are all perpendicular to this fixed vector u. So for example, this single thing is perpendicular to u because if you dot -3, 2, 0 with 2, 3, 5, well you'll get -6, +6 plus 0, that's 0. And if you dot -5, 0, 2 with 2, 3, 5, then you get -10 plus 0 plus 10, so that's 0. So certainly these two vectors are orthogonal to u. And now every single linear combination of these two vectors is orthogonal to u. So the upshot here is the following. When you look at all of the vectors that are orthogonal to a fixed vector, right? All of the vectors that are orthogonal to a fixed vector, those vectors, when you collect them all, form a plane, right? And that plane is spanned by these two things. So you should, when you work this out, you'll always come to this kind of thing at the end. So you want to memorize that. The set of all vectors perpendicular to a given non-zero vector is a plane. And so here's sort of the verification of that fact. All right, in the last example, we showed that if you've got one fixed vector, then the set of all vectors that in R3 that are perpendicular to this one fixed vector, that'll sweep out a line. When you collect all of them, it'll sweep out a plane. So now let's do the opposite. And we showed that the set of all vectors perpendicular to 2, 3, 5 was the span of these two vectors. Now let's do the reverse. Let's suppose we're given these two vectors, right? So two vectors, and we want to find all of the vectors that are perpendicular to these two. So really, what's that going to be? Well, the set of all vectors perpendicular to these two should be one single line, or the span of one single vector. So all of the vectors perpendicular to a single vector is a plane. All of the vectors perpendicular to a single plane is just a line. So that's what this should show at the end of the computation. So how do we find all vectors perpendicular to two given vectors in R3? it should be roughly the same as that vector 2, 3, 5 that we started out with last time, but let's see if that's right. So if V is perpendicular to both of these things, let's give V a component name. So we'll say it's x, y, z. So if V is perpendicular to this thing, then that means negative 3x, right? That means the dot product of this thing and this thing is equal to 0. So negative 3x plus 2y plus 0 should be equal to 0. So here's one homogeneous linear equation. And now x, y, z is also perpendicular to this thing, so orthogonal, so the dot product should be 0. So negative 5x plus 0y plus 2z, orthogonal means they should be equal to 0. So now here's another homogeneous linear equation. And now what do we have? We have a system, a homogeneous system of linear equations. So now let's go ahead and write this thing as a matrix. I'll go ahead and augment it with 0 so that we're aware that we're solving an equation. So now I'm going to take this thing and put it in reduced row echelon form. So that's what all of this is, right? Take this matrix, put it in reduced row echelon form, and now you can see exactly what the solution is, right? So x, y, z is going to be equal to, right? X, y, z is going to be equal to, so this says that x, so we've got pivot, pivot, free column. So x is going to be 2/5 times t. So 2/5 times t. Y is going to be 3/5 times t. So 3/5 times t. And then z is just going to be the free variable t. So now we know that if x, y, and z, this vector v, is perpendicular to both of these, then here's what x, y, z needs to look like. So now we can see that x, y, z, so this vector v is now of the form t times 2/5, 3/5, and 1, right? I just factor a t out of this thing, and then I get this thing. But as t runs through all of the real numbers, certainly t can be equal to 5, and so now this is the same thing as 2, 3, and 5 when t runs through all of the real numbers. So what does v have to look like if it's perpendicular to these two things? That means that v belongs to the span of this one single vector, 2, 3, 5. And that's what we expected, because this is basically just the reverse of the last problem. So if you hand me one single vector, you can find all of the vectors that are orthogonal to that one single vector. It should be a plane. So it should be, at the end, your answer should be the span of two non-parallel vectors. If you hand me two vectors in R3 to start with and say, what are all of the vectors in R3 that are perpendicular to both of these, right? So perpendicular to both of these at the same time, then that object should be a line, right? So all of the vectors perpendicular to a plane, that should just be a line. And that's what this shows. This is the span of a single non-zero vector, and remember, the span of a single non-zero vector is just a line. So all of the vectors perpendicular to these two, that's a line, right? This is all of the vectors perpendicular to the plane spanned by these two things, so you just get a line. And reverse. The set of all vectors perpendicular to a single vector is a plane.